everyone. Today we are going to do an experiment in which we are going to learn how to calibrate laboratory glassware, and we're going to learn about precision and accuracy. So today's goal is we are going to calibrate 4 pieces of glassware, and we'll talk about what calibration means in a minute. So the 4 pieces of glassware we're going to use will be a beaker, a graduated cylinder, a 20 milliliter volumetric pipette, a 5 milliliter volumetric pipette, and once we've calibrated those 4 pieces of glassware, we want to use the most precise piece of glassware amongst those 4 to determine the density of an unknown salt solution. So the glassware we will use will be a beaker and a graduated cylinder, and they're pictured here. You've probably used those before. You might not have used volumetric pipettes. So these pipettes, there's a picture of a 20 milliliter volumetric pipette here. And these pipettes can deliver whole milliliter amounts from 1 milliliter up to 100 milliliters. And there's only one marking, so you can only deliver that amount. So they're very good for reproducible delivery of liquids. And what's nice is they can be used both with aqueous solutions and organic solutions. We have some measuring apparatus that don't work well with organic solutions. So these are nice because they're glass and you can use a wide variety of solutions with them. When you use them in the lab, you will look at them and you'll see at the top there'll be a little designation that says TD, which is to deliver. And what that means is that the volume is transferred to your container and there will be a drop in the tip and you're not going to blow out that last drop. And the pipette is manufactured in the way that it will deliver the accurate amount of volume without having to blow out that final drop. So what we need to use our pipettes are pipette fillers. So we need some means of drawing the reagent into the pipette. So I'm sure none of your professors have ever done this, but I've had professors in my lifetime who used to mouth pipette and sort of use the pipette like a straw. I'm sure you can appreciate that's very dangerous, and we will not be doing that in lab. Later we will be using Pesture pipettes. We'll use latex bulbs for those. But the volumetric pipettes I just showed you, we will use these mechanical pipette pumps. You want to be really careful not to get any solution in the pipette filler. But if you do, let one of your instructors know and we can help you take it apart and clean it. So these are the pipette fillers. We'll be using the red ones. For the smaller pipettes, like the 1 ml pipettes, we use those in my research lab. We would use the blue pipette fillers. So in this PowerPoint, I have a link to the pipette video. I'm not going to show it right now because it's on Sakai, and I sort of jokingly refer to Dr. Baer, so he recorded the video before he retired, and I refer to him as the headless chemist because in the video you cannot see his face, and he did that on purpose because he wanted the pipette to be the star of the show. I encourage you to watch that video so that you'll learn how to use the pipette properly. So back to calibration. What does calibration mean? We want to know what the volume is actually delivered by each type of glassware. So we can try to deliver 20 milliliters, but we want to know exactly what we are delivering. So determining what that actual volume delivered is referred to as calibration. So this is an accuracy measurement because we'll be able to compare how close the measurement that we get is to the true measurement, or 20 milliliters. But the other thing we want to do is we're going to do 3 trials, and we want to see how consistently and reproducibly we can deliver that amount of solution. So that is a precision measurement because it refers to how close the values are to one another. And the other thing we want to determine is, of those 4 pieces of glassware that you will be provided with, is one of them more precise than the other 3? So how will we calibrate our glassware? Well, what we're going to do in the lab is we'll make 3 attempts to deliver 20 milliliters of water using the beaker, the graduated cylinder, and the 20 milliliter volume pipette. We have a 5 milliliter pipette, so you're just going to use 5 milliliters with that. And the way we calibrate this is that we can determine the mass of the water that we deliver. And we can determine that pretty accurately because we have balances that weigh to 3 places past the decimal. The other thing we know pretty accurately is that we can measure the temperature of the water in the lab, and we have a nice table on Sakai that has a very accurate determination of the density of water at that temperature. So what we can do then is we can use the density equals mass over volume and solve for volume to determine the actual volume that we've delivered. So the easiest way to do this is to make the 3 attempts our container that's going to hold the water that we're going to be weighing is called an Erlenmeyer flask. So what we're going to do is we're going to use a beaker to measure 20 milliliters of water. We're going to weigh an empty Erlenmeyer flask and then transfer the water into the flask and then weigh it again. And then we can determine the mass by subtraction. And then we're going to do that 3 times, and you don't want to empty the flask in between. It's not necessary, and it makes our measurements easier if we don't do that, and I'll show you why that's true in a minute. So here's our balance, and the first thing that you do when you see the balance is there'll be either a T or a tear. That sets the balance to 0, and then you'll want to put an empty Erlenmeyer flask. Oh, that's the tear button right there. And then you'll want to put an empty volumetric flask on your on the balance, and you see here it weighs 81.444 grams, so you'll want to write that value in your notebook. Then you're going to use a beaker to measure 20 milliliters of water and then pour that into the flask and then weigh the flask again. So here I am, I have a large beaker with lots of water in, and there's my beaker. I have a 100 milliliter beaker, and I'm trying to measure 20 milliliters of water. So there's a little 20 ml mark there that you can see right here. So I've tried to measure 20 milliliters the best I can. So notice that I take my Erlenmeyer flask off the balance, and I pour my 20 milliliters of water in there, and then I put it on the balance. You don't want to transfer the water on the Erlenmeyer flask when it's on the balance, because if you spill it, you could damage the balance. So we don't want to do that. So here I am. I've got my flask. Now it has 20 milliliters of water in it, and it weighs 99.544 grams. I write that number down. So what we want to do then is we want to repeat this without emptying the flask. And this goes to precision because we want to do this 3 times. So there I am a second time measuring 20 milliliters of water, and I pour my 20 milliliters of water into the flask. So now it's got 40 milliliters of water, and now it weighs 118.461 grams. I write that down. And then I do it again. So now it's got 60 milliliters of water, and I weigh that, and now it weighs 138.581 grams. So now my Erlenmeyer flask container has 60 milliliters of water in it because I've done it 3 times. So you want to use the same balance throughout the experiment. Make sure, again, don't transfer the water to the flask while it's on the balance because the water could damage the balances. So what I'm going to have in my table then is up here, 81.444 grams, that was the mass of my flask when it was empty. And then when I put the 20 milliliters of water in the flask, it weighed 99.544 grams. So if I want to know what the water weighs, all I have to do is subtract. But for my second trial, all I have to do is just write down that 99.544 grams here, and then that was the mass of the flask when I weighed it the second time. And then again, I do the subtraction. And then the third time, again, I just take this number and write it down here and do the subtraction. So that's the mass, 1, 2, 3 of my trials. Remember, I was trying my best to measure 20 milliliters of water, and that's what the 20 milliliters of water weighs. So again, you don't have to reweigh the flask because what we want to do is we want to measure not 20, 40, 60, but 20, 20, 20 milliliters of water. So now I know the mass of the water. So there's a nice table on Sakai, so you should look that up and determine the density of the water. So you'll have to use a thermometer and measure the temperature of the water to the nearest 0.1 degrees Celsius. And then once you have your masses and the density, you can use the density formula to determine the volume that actually was measured by the device. Not what you tried to do, but what you actually did. And that's called calibration. So I've calibrated my beaker. That's the volume that the beaker is actually capable of delivering. So if I do that, so if you look at this table now, so those are my masses. I've used the density formula here to determine the actual volume. And then the next thing that I did is, because I did 3 trials, I determined the average, and I also determined the standard deviation. So the average, when I compare it to 20, will give me an accuracy measurement. The standard deviation will give me a precision measurement. How reproducibly could I do this 3 times? Now I want you to notice that this is not reported correctly. So what I have to do is I have to tell you how to calculate the standard deviation, and then we're going to correct it. So what we need to know is the piece of glassware with the smallest standard deviation is the most precise. So the smaller the standard deviation, the less variability there is between the 3 measurements. That's what standard deviation means. If there's a really large standard deviation, there's a lot of variability between your 3 measurements. So what does it mean, and how do we calculate it? So suppose I have the sample data set. Maybe I used 5 tries to measure the volume of a certain sample, and this is what I got. So I would calculate the average and the standard deviation. So the average, or the mean, is 7.2, and then I use a symbol plus or minus 0.5 milliliters. So I'll get to how I calculated that in a second. Notice that there's the average, 7.2, and then the symbol plus or minus 0.5, and then milliliters, the volume, goes at the end because the standard deviation and the average always have the same units. So that's the mean, or the average, and that's the standard deviation. So the units go at the end. So since you're doing plus or minus, whenever you add or subtract something, they have to have the same units. So let's look at what this means. So this is a graphic that I made. So if my average, or my mean, so it's pronounced X bar, it's an X with a line over it, so we pronounce it X bar. So remember, the mean, or the average, was 7.2. And we said plus or minus 0.5. Well, 7.2 plus 0.5 would be 7.7, and 7.2 minus 0.5 would be 6.7. So what this means then is that if I have 7.2 plus or minus 1 standard deviation, the standard deviation being 0.5, then what the statisticians would tell me is that 65%, and I'm going to try and shade it here, 65% of my data measurements will lie within 1 standard deviation. If all of the measurements I take fall along this nice Gaussian or bell-shaped curve, then 65% of my data should lie within 1 standard deviation. Well, what if I have 2 standard deviations? So remember, my standard deviation was 0.5 milliliters. So 2 standard deviations would be 1 milliliter. So 7.2 plus or minus 1 would be between 6.2 and 8.2. And the statisticians would tell me that 95% of my data should lie within 2 standard deviations. Well, how about we go to 3 standard deviations? So 3 standard deviations would be 1.5 milliliters, so now we're between 5.7 and 8.7, and now 99% of my data points should lie within 3 standard deviations of the mean. So that's what we mean by standard deviation. So if you have a curve that's sort of long and sort of big and fat, that might mean you have a large standard deviation, but picture one where the Gaussian curve, the bell-shaped curve, is very, very narrow with a really small standard deviation, and that would indicate that you had more precise data. So the information that we get from the standard deviation is a smaller standard deviation means that there's less variability in the data. That means when you made your measurement, you made it very reproducibly. So the data are more precise and the data are more reproducible. If we have a large standard deviation, there's a lot more variability in the data. They are less precise, and that means when you made your measurements, you didn't make them reproducibly. So the smaller the standard deviation, the more precise the data. So what that means then is we have to go through our calibration. I show you how to do it with the beaker, but we're going to have to use all 4 pieces of glassware and calculate the averages and the standard deviations. Now I want you to use the standard deviation calculations using a calculator or a spreadsheet. I'm going to show you how to do it by hand, but this is something that your calculator knows how to do. Even the most simple calculators are capable of doing this calculation, and this is something that is going to be very helpful if you know how to use your calculator to do it. So we'll help you with that if you're having trouble. So this is the built-in function of standard deviation that's built into your calculator. So I'll walk you through this. So S is the standard deviation. So what this means is that this big sigma here means sum. So this is the n number of values we have starting with the first and going to the last one. This is your mean, which is x bar, and this is just x sub I. So that's just one of your data points. So you sum the differences between your data point and the average, square them, divide by n minus 1. So n is the number of measurements minus 1, and then you take the square root of the whole thing. So going back to that data set that I showed you, where I had these 5 measurements right here, and at 7.2 is the mean, what I'm doing is I'm subtracting each one of my data points from the mean, and then I square it, and that's nice because you don't have to worry about negative numbers. And then I add them up. That's what that sigma means. It's a sum. You add them up. And then I take the that value and I divide. I made 5 measurements, so 5 minus 1 would be in my numerator. And then I take the square root of the whole thing, and I get 0.543. But we want to be able to express this properly. That wasn't expressed properly. This is how we do it properly, and it's very easy to remember. The standard deviation has only one significant figure. You'll be learning about significant figures in class. So the standard deviation has only one. And once you know how many significant figures the standard deviation has, then you can figure out how to express the average. Because the average and the standard deviation should be expressed so they have the same number of places past the decimal point. So what I did then is I took that 0.543 standard deviation, and then I have to round it to 0.5 because I can only have one significant figure in my standard deviation. So that goes only one place past the decimal point. So that's why I have to express my average as 7.2. So I have 7.2 plus or minus 0.5 milliliters. That's the average plus or minus the standard deviation. So back to the data right here. Remember I told you that this was not expressed properly. Well, here we can see that the standard deviation is pretty large. So we have 1.019. Well, I remember I can only have one significant figure. So 1.019, that rounds to 1. Well, that doesn't have any places past the decimal point, so that means my average can't either. So 19 plus or minus 1 is how I have to express that. So the next thing we're interested in is the accuracy measurement. So that's percent error. So use this formula here. It's the observed value minus the accepted value over the accepted value multiplied by 100. So this is 19, so I would take 19 minus 20 divided by 20, multiplied by 100, and I get minus 5%. So that minus sign means that my observed value is lower than the accepted value. Okay, so you've done all your calibration for all 4 pieces of glassware. You've calculated the mean and the standard deviation, and you've done it properly. So now you have to choose the piece of glassware that most consistently delivers the calibrated volume. And then that is what you should use to determine the density of your unknown, because part of your grade is going to be based on how well you do that, and you would want to get the best results possible. So Another piece of information that we'll have that we need to do is something called the relative standard deviation, because for our 4 pieces of glassware, we measured 20 milliliters with 3 of them, and then we also had a 5 milliliter pipette. So what a relative standard deviation is, it normalizes measurements of different values. So if you have a 5 milliliter pipette and say it's off by 0.5 milliliters, that's less precise than a 20 milliliter pipette that's off by 0.5 milliliters. So in the relative standard deviation, you just take S, your standard deviation, multiply that by 100 and divide it by the mean, and that will give you the relative standard deviation. So I'm summarizing my data right here. So notice here that everything has been expressed properly. So this is another data set, not the other one that I showed you. So I used a different beaker, and I had 19.7 plus or minus 0.6, 19.5 plus or minus 0.2. Here I have 19.99 plus or minus 0.01. So here I'm able to go 2 places past. Here I'm able to go 3 places past because I can do 4.981 plus or minus 0.007. So this gives me the relative standard deviation because here I am measuring 20, where here I'm only measuring 5. So this gives me the relative standard deviation, and here's my percent error right here. So the percent error just tells me, well, how close was I to 20 milliliters here? How close was I to 5 milliliters here? But when you're trying to figure out which piece of glassware you should use to measure your unknown, you need to look at the most precise piece of glassware, and that's going to be based on your relative standard deviation. So here it's 0.06. That is the most precise piece of glassware. So I should use the 20 milliliter volumetric pipette to measure the density of my unknown. Okay, so now what you do is what you've done before, same procedure. Take your 20 milliliter pipette and take your unknown and measure the mass of your unknown 3 times. So you'll know the mass, and you also know the volume. It's that calibrated volume that you determined. So you're not going to divide by 20. You're going to divide by whatever the volume you calibrated was. And then you figure out the density. And you'll report the mean and the standard deviation. And part of your grade is going to be based on your results. So you're going to carry out all your calculations in the lab notebook. We're going to give you a result sheet, and you're going to fill it out and return to the instructor before you leave. That is the only time that we're going to do something like this, because as we explained to you before, we want you to learn how to write laboratory reports. So we're going to scaffold this process a little bit and learn as we go along. So by the time we get to the end of the semester, you'll be writing high quality laboratory reports. So today's focus is learning how to organize your data in tables and how to report your data properly. Make sure you come to lab dressed properly. We are not using anything particularly dangerous. Our unknown solutions are salt solutions, but we want to get in good habits. So we're going to provide you with a pair of safety goggles. Those are provided for you by the department, and they are yours. You should bring them to lab every week, and in fact you should keep them because you will need them throughout your chemistry career. The American Chemical Society specifies neck to knees, which means that the neck to knees need to be covered. So we are going to provide you with lab coats, which will cover you to neck to knees. But what we want you to do is from your knees on down to your toes, there shouldn't be any skin exposed there either. So that means you need to be wearing long pants and socks, and you need to be wearing shoes that cover your entire foot. So no exposed skin at all from your neck to your toes. I know that flip-flops are kind of nice and comfortable to wear when it's hot out, but you cannot ever wear flip-flops in the lab. So if your footwear is not appropriate, if you're wearing flip-flops, if you're wearing shorts, if you're wearing pants and you're not wearing socks, we're going to have to send you home to change, and nobody wants that. So make sure you come to lab dressed properly. You can't chew gum in the lab. That kind of falls into the no food or drink. You can't wear headphones either. If you want to listen to music, you can negotiate with your professor and your lab mates to have music on in the lab if you want. Some professors like it, some don't. You should talk to them about what they want. But having headphones removes you from communicating with your fellow classmates and with your instructors, and it maybe means if there was any kind of safety information given, you might not hear it. So you can't wear your headphones in the lab. We're going to be using waste containers. We will show you about that. So unknowns should be disposed of in a waste container and not thrown down the drain. All right, so that's it for today, and we will see you in lab.